we're going to finish up the last topic in this unit. I should also let you know that next week there's going to be a couple of review lectures. So Yi-Hong will be back on Tuesday morning to tell you a little bit about what you need to know from the first part of the course, and I'll be back here for Friday next week to give you sort of an overview of the entire course from the numerical methods point of view. Okay, I'm going to give you a demonstration of this naive Gaussian elimination a little bit later. That's just there to remind me. You can have a bit of a play with that yourself. Unfortunately, it was designed to come up with a really nice flashy interface on the MATLAB screen where everything's appeared in different colours, and it no longer seems to work, and I've got no idea what the problem is. So we're not going to have a flashy demonstration. It's going to be quite a simple one. So you'll actually see, I hope, as a result of this lecture, that programming naive Gaussian elimination is actually fairly simple in terms of how many lines of code you need. There's not very many lines of code. It seems like a complex process, but when you understand how things actually fit together and you abstract the patterns, it's actually quite simple to code it up in about 10 or 15 lines. One of the key things about this kind of work that we're doing in this unit, the second half, is that programming stuff up is usually the only way of understanding how things work. You can sit there and sort of intellectually look at someone else's code and say, oh, yeah, I can see what's happening, this is happening. But until you actually sit down from scratch and try and do it yourself, you don't actually have a good understanding. Or at least most people don't have a good understanding. It's only going through that process of making lots of mistakes and thinking it's not working, I don't understand, and then eventually figuring out why not, that you actually begin to understand how coding works, especially for things like numerical methods. So the naive Gauss elimination that we discussed last time, we'll be doing a bit more of that today. It uses loops and some vectorized calculations. We'll come to that in a minute. But these concepts are really useful MATLAB concepts. So we're actually going to do that. We're going to spend much of today's lecture on figuring out how we'd actually code this thing up. I'm going to try and take you through it slowly so that hopefully it makes sense. And if individual steps aren't making sense, then someone should interrupt me and say, I don't understand that, okay? I don't mind being interrupted if you've got a question. Okay, so there's basically 3 steps. Let's assume that we've got a matrix system that we're trying to solve. It's AX is equal to B, and we know what A is, we know what B are, and we're actually trying to find X. That's ultimately why we would want to do this thing. We're trying to find what X is. So the first step in our little bit of pseudocode, the algorithm if you like, is we're going to make an augmented matrix from A and B. We'll come to that in a minute. We're going to go through the process then of forward elimination. Remember that process was putting a whole bunch of zeros underneath that diagonal. Once we've done the forward elimination, we then do the back substitution. We go back up the equation and actually progressively solve for the unknown variables X. Okay, so that's Gaussian elimination. The way we do it, we're going to do it here in MATLAB, is by augmenting these things. In actual fact, you don't have to do that, but it's actually a very convenient way of doing things. It also helps to stop you making mistakes. Okay, or it guards against it. So what we're going to do is we're going to take these 3 steps and we're going to slowly expand them so that we can eventually go from here into something that looks like a piece of MATLAB code. Well, the first step, making the augmented matrix, it's hardly a step. Aug equals bracket A space B bracket. We now have an augmented matrix that has the elements of A going across here, and then it's got the column vector B stuck across there, and it's just one matrix. Okay, it's no longer a square matrix. A will be a square matrix, B will be a column vector. This is no longer a square matrix, but that doesn't matter for what we're doing here. Good programming practice says you need to check that A and B matrices have the right size. First of all, A needs to be square, and B has to have the same number of rows as A does. If it doesn't, and you try and do something like this, well, I don't quite know what will happen. I'm guessing you'll get an error message, but regardless, you're not going to get a solution. Okay, so good programming practice says I need to check that these two things are compatible with each other. Okay, doing these little checks, even though it's a few extra lines of code, is going to save you time in the end, because you'll always eventually make some kind of mistake like this, and sometimes it can take you an hour to figure out what you've done wrong, and it might be just one extra value in a vector, and you've wasted an hour where if you'd spent 1 minute typing in a little check, you've saved yourself an hour. And I'll be honest, it might be a lot more than an hour. It could be a couple of days, depending on how fast you program. Okay, so the first step, creating the augmented matrix, is simple. Steps 2 and 3 are somewhat more complex, and I think hopefully you'll remember that from what we did last lecture. So we're not going to try and do them simultaneously. We'll do the forward elimination first, expand that out. Once we've got that sorted out, we'll come to the backward substitution and do that. Okay. And this process that we're going to go through today is exactly the kind of way I would recommend you try and do things like this. Breaking things down into smaller and smaller pieces so that each of the pieces is actually not so daunting. If you try and look at the whole thing as one, sometimes it can appear to be so complex that you can't even get started. If you break things down, then each of the steps starts looking simpler. Okay, so let's have a look. We're going to look at a little 3x3 system, the matrix A, A19, A12, etc., and the column vector B1, B2. We've augmented it to get this augmented matrix here. And if you recall, the first step in the elimination is to take this first value here, which we call the pivot. And for the first row, the pivot is A11. And this whole row is referred to as the pivot row. It's just the variable, it's the row, in which the pivot sits. Okay, we always start in the first row. You're going to take that, and for each of the rows below the pivot row, so in other words for row 2 and row 3 in this particular case here, we're going to calculate what we called a normalization factor, and we'll come to that again in a minute, and then we subtract a certain amount of the first row from the second row. And we aim to do that so that we can get this variable here to be equal to 0. Okay, so we're going to figure out how much of this first row we need to subtract from the second row in order to make this thing 0. Then once we've done that, we move to the next row down and we do exactly the same thing here. The normalization factor is going to be different for the second row and the third row and the fourth row. And so we need to calculate it for each different row. Once we've got down to the end, we've got a 0 here and a 0 here. We're then going to move down to the next row. This then will be the pivot. These things are already 0 because of what we've done before. We're then going to calculate, now for this system we've only got to do it for one element here. We've got to calculate what multiple of this row here we subtract from this row to make this thing 0. Okay? We never need to pivot around this point for a 3x3 system because we've gotten to the end by the time we've done the second row. But the logic would be something like move down to the next row, do the pivoting. If this is not the bottom, if this is not the bottom row, do the pivoting, then go up and go down to the next row. Okay? Do the pivoting, move down. Is that the last row? No. Go up and do another row. Is this the last row? Yes, it is. Then we don't do anything else. So you need to somehow take that into account. Now, for something like this, you would almost always use a for loop because you know how many rows your matrix has. It would be possible to use a while loop if you wanted to, but I wouldn't recommend it. You know what's going on. Make life simple for yourself. Okay, so for the forward elimination, I've just expanded out what we had on the previous slide a little bit more. Steps 2 and step 3 are basically going to be done in a for loop. That's the whole process of shifting one row down each time you do a new pivot row. Okay, so steps 2 and steps 3, and then we do a check to see whether at the end or not. If not, do another step 2, step 3, etc. The other thing we actually notice that these commands here, that's also going to be a for loop, but it's going to be a separate for loop. It's going to be a for loop that's inside this outer for loop. So this for loop out here steps down the rows. It goes to row 2, to row 3, etc. This loop here does the lines underneath the current pivot. So you've got to have that sort of concept in your head where you're looking at two what are called nested loops, and these will both be nested for loops. Okay, so let's expand this out a little bit further from the previous slide. We're going to start at row 1. That's the first row we're going to pivot. And we're going to go all the way down to row n minus 1. Because remember, row n, we don't need to pivot because we've already got to the last point. There's nothing to do there. So our for loop is going to be for p is equal to 1 to n minus 1. We're going to do some stuff. We're going to do the pivoting. Okay, so we do that for each of those pivots. Okay, so for the moment, we'll just leave that written like that. So this outside for loop is the for loop that takes us down sequentially into the rows of the matrix to do the pivoting. Okay, so it's going diagonally down, because remember, once we've got to a certain point, everything to the left of the pivot is already 0. So we don't have to do anything to those things. Oops. Okay, so just going back. So we've got this loop here. This is the outside loop. We're going from row 1 to row n minus 1. Not having much luck with my keyboard today. For a given row, so we're pivoting row P now. So we've pivoted that row, we've pivoted that row, we've pivoted that row. We're sitting down here somewhere now. We're going to pivot on that row. The only rows we have to modify are rows that are below it. We don't have to do anything to rows that are above it. Okay, so this is the outside loop going down the pivot rows. This is the loop that says, okay, which rows do we have to change something on? Well, for r is equal to p plus 1, in other words, the row underneath the pivot row, all the way to the end. And the end in this case is n. So we're going to go for each of those things below. What we do is we calculate the normalization factor and subtract the pivot row multiplied by that from the current row. Is that making sense? A few people are nodding. No one's shaking their head. Someone shook their head. We'll leave it. Okay, so basically for each row below the pivot row, we are basically telling ourselves we needed a for loop. That's this for loop here. So the loop is nested inside the pivot loop. This idea of nesting loops is a really important one. And there's in this particular case, we only need to nest 2 levels deep. But there's no reason for other things that you might want to do. You might have 3, 4, 5, 6 levels deep. So there are complex things that you will do with MATLAB whilst you're at this university, which are far more complex than this. Okay, and this idea of nesting loops one within the other is just an idea that you need to get used to. The bounds on the loop can always depend on the bounds of an outer for loop. They can't depend on the bounds of an inner for loop. Okay, so this one here couldn't depend on R, because you'd be messing up R in the course of this computation here. So whilst this loop here can depend on P, this one here, or these conditions here, cannot depend on R. Okay, so we've got to this point here where we've got the 2 loops, so we've got the basic structure of what we want to do. Now we just need to calculate these 2 things in here. So we've started off with words, and gradually we're replacing the words with bits of MATLAB code, little individual lines. So calculate the normalization factor. Well, we know that the normalization factor is for row R, when we're doing pivot row P, it's going to be the value that's underneath level P. So in other words, we're in row R, but we're in column P, and this is the value we're trying to get rid of, trying to make 0. We needed to divide it by the pivot value, that's the diagonal value, because we're again going to multiply the pivot row by this factor here and subtract it from the current row. So basically what we've got is augmented RP is sitting here, and this is PP up here. What we're going to do is we're going to say this row, this value here, is going to be equal to itself minus that divided by that times the top one here. So it's actually going to be equal to 0, just by the way we've put it together. So this is calculating the factor. This then is actually doing the subtraction, such that org RP is equal to 0. Sloppy writing. Okay, but what we want to do is we actually want to do that not just to that value. We can't do something just to one value in a row. We've got to do it to the entire row. Okay, because what we're doing is we're subtracting a fraction of one equation from another equation. That means you've got to do the same thing to every entry in the row. You've got to multiply it, divide it, subtract it, whatever you're doing, but you've got to do the same thing. So we're going to do it to row R, but we're going to do it to every column in row R. So that's kind of clear. We're not just doing it to the one value. We calculate the factor based on that leading value, but we then subtract the entire, or a fraction of one row from another row. So the question is, I've said here, well, this is a nice way of actually doing it to an entire row using a nice MATLAB syntax, which is using a colon instead of a range, or instead of doing it. I mean, what you actually could do is you could put this, if you wanted to, inside another for loop. For S is equal to, make sure I get this one right, P to N. Org RS is equal to org RS minus factor times org PS. Okay, so in actual fact, we could nest this in 3 loops if we wanted to, but it's much easier to write it like this. We're just doing it to the entire row. We just use that colon notation. The reality is our augmented matrix looks like this. If we're sitting at this point, row 2, and we're trying to do the pivoting here, we've already got zeros in these 2 spots here. We don't actually need to subtract anything from them. I mean, the reality is, if we subtract any number of zeros from this 0 here, we're still going to end up with 0, so it's not going to hurt us if we do it, but it's a little bit inefficient. Now, for a 3 by 3 matrix, who cares? But if you've got a very much bigger matrix, that could actually make quite a bit of difference in terms of the amount of time it takes to do the computation. In fact, you save yourself a factor of 2 in this particular step if you only do the elements that you actually need to. So the way in which we do that then, we don't need to actually subtract those values. We only need to worry about these ones here. So what you can do, instead of putting a colon in each of these places, you just say, okay, I want to go from column P to the end. Now the end in this case is n plus 1. And we called it NB because that's the value, the column value, where the B vector has been stored in our augmented matrix. So that's just a nice bit of notation to help remind you what this last thing actually is. I mean, you could call it anything you like, but NB says, oh, that's the column value for where B is stored in my augmented matrix. Okay, so this here is, it's a more efficient way of doing it. And if you have a very big matrix, you can actually save some time doing it this way. So in terms of MATLAB, the forward elimination, ignore all of this stuff, ignore the comments, although we do want to see comments because they help remind you what you've done. There's 1, 2, 3, 4, 5, 6 lines of code. 6 lines of MATLAB code does the forward elimination for you. Okay? Pretty easy to code up 6 lines, but if you want to sit down there with even a 10 by 10 matrix and do the computations by hand, it's going to take you a very long time to do them. So what we've done now, we've created the augmented matrix. We've done the forward elimination. The only step we've got left is the backward substitution. So just to remind ourselves, for the 3 by 3 system we're looking at, it looks like the augmented matrix looks like this. Now, just note there's just a bit of notation here. We've got a prime here, a prime here, and a prime here, and then a double prime here and a double prime there. And if we carry this on to the 3rd row, there'd be a triple prime and then 4 primes, etc. The only thing I'm trying to get across by doing this is that this entry, A22 prime, is not the same as A22 in the original system because we've modified it by subtracting a fraction of that top row. This thing is not the same as A33 because we've actually done a couple of different things to that, and so on. So this is not the value in the original system, this is the value once you've done the forward elimination. Those are the only reasons we got those primes there, just to make sure that you understand that difference. Okay, so this is our 3 by 3 system. We need to do the back substitution. I think it's pretty obvious. From this bottom row here, what this equation is actually saying is that A3, 3, and now there's a double prime there, x3 equals b3 double prime. That's what this effectively says. So we just divide both sides by A33 double prime, and we've got x3. So the very first step, and I've left the primes off here because it's really clumsy to write them in normal text, but I think you'll understand what I mean. x3 is equal to b3 divided by A33. We've got the first of our values. Once we've got the first of our values, we then move up one equation. This bit of code here is basically saying that A22 prime x2 plus A23 prime x3 equals b2 prime. Well, we know what x3 is. We've calculated it here, so we can move this across the right-hand side and then divide by A2, the whole lot by A22, and we end up with that equation there. And so on. By the time we get up to the top equation, we know what x2 is equal to, we know what x3 is equal to, we move them to the other side, and we divide by A11, which is the pivot element. So this process of back substitution, you have to do it one row at a time. You can't do it, there's no fast way of doing it, because the next value depends on the previous value. In fact, all the previous values. But, I don't know, looking at that, can you kind of like see a pattern that's emerging? And I think it's really important when you're doing programming, especially for things like this, that you start identifying patterns. Because it's in that pattern identification, that pattern recognition, that you begin to then understand, oh, okay, I can generalize this. I can actually write a generic formula that's going to describe what I have to do here. So we'll go through that in steps, but just as a general rule, you want to get good at this stuff, look for patterns, because patterns will really tell you a lot. Well, the first row is, I should say the last row, this one here, is very simple. We always know what that is. It's just the last value is equal to the right-hand side divided by the pivot coefficient at that point. So we're sort of going to exclude that from our generic algorithm because it's always the same. Let's just look at these two down here. The first thing to notice is, well, we're going through the pivots, but we're going back up the other way. We're now moving up in that direction. A33, A22, A11. Well, it seems pretty obvious that we can use a for loop to do this, but it's going to be a for loop that starts at the end and goes back to the beginning rather than starting at the beginning and going back to the end. So, purely the pivot code, you do this in MATLAB for P, goes from n-1. Remember, we're going to exclude the very last row. P goes from n-1 in steps of -1 all the way back to 1. Okay, so we're going to subtract 1 from n-1 each time until we eventually get to 1. And the pivot is just augmented matrix PP. Not only are we going backwards with the pivots, we're also going backwards in the B. We're going up here with the B's that we use. Okay, so our value of xp is going to equal, oops, wait a second, where am I? Okay. You sorry? Yep, I confused myself. That's B. Okay? In fact, that's BP. So remember, we stored the column vector B in the right-hand column of the augmented matrix. So going up here like this is equivalent to writing aug P, NB. We've got to subtract some extra stuff. We don't know what that extra stuff is yet. We don't have a general idea of what this looks like yet. So we're just going to leave it as, well, I know we've got to subtract something, but we'll figure that out in a minute. But what we do know is we have to divide by the pivot element. So what we're starting to do is we're starting to fill out the formula. We know that the formula always looks like the B value, which is given in here, minus something divided by the pivot value. That's this general formula that we're beginning to pick out from just looking at what we've done by hand. And another tip, when you're trying to figure out algorithms like this, do a little 3x3 system or a little 4x4 system, just so that you begin to pick out those structures. If you don't actually sit down and do that, then it's really hard to pick the structures out in the first place. Okay, so the only bit we've got left is this bit here. And I think we can kind of see that there is a pattern emerging from that. First of all, if we're looking at this x1 down here, all the A coefficients start with 1. So it's A12, A13. And the 2 always matches with the variable. So the second element always matches with the variable. So this is the value for x2, the coefficient's A2, or A23 I should say, and it's multiplying x3. So it's something that sort of looks a little bit like, Aij times xj. I mean, there's going to be a sum of things there. Let's just make that a bit more explicit. Let's just make them all have, make this actually equal to a sum, and we're subtracting that sum from this variable here. And if we actually had, if we had another row in here, this would be an A14 times x4. Okay. 3 by 3 system, obviously we don't have that. Now, it's not necessarily obvious that this thing's a matrix multiply, but I think in a minute we'll see that it is. Let's actually just go back graphically to the augmented matrix that we're looking at. For row 2, the thing that we're trying to calculate is this thing here, and it's just equal to A23 times x3. Well, that's really just one number minus another number. It's a little bit hard to see what you're doing there. But if we go to this row here, then it's starting to make a little bit more sense. Write this as a row vector multiplied by a column vector. That's what this term here looks like. And in actual fact, this term looks like it as well, except the vectors are only 1 unit long, so they're not really vectors. So we can write this step here in a general sense as, okay, we're in row P. We're going to look at the coefficients that go from P plus 1 to the end, in this case A12 to A13, and we're going to be multiplying those by this vector of unknowns that we've already calculated, and that is just written as x P plus 1 to n. So this thing here is that thing there. Absolutely one-to-one correspondence. And so we've extracted this pattern here just by looking at a small case example. So we've basically done everything. The backward substitution for MATLAB then, let's actually just allocate. We know it's got to be the same size as B, the vector of unknowns. Let's just allocate it equal to 0 so that we pre-allocate the memory. If we don't pre-allocate the memory, it get very inefficient because each time it needs to add another one to the end, it's got to create some memory, copy the whole lot across and delete the first one. You know it's going to be the same size as B, so allocate it beforehand. That's just good programming practice. Always start off using calculate the last value by itself. So xn is equal to the column value B divided by the pivot value at n. That's just that last equation. Then, this is the back substitution. 3 lines of code. We're going to go from pivot row n minus 1 up to pivot row n in increments of minus 1, so n minus 1, n minus 2, n minus 3, etc., down to 2 to 1. And the new value of x is equal to the value of b minus this vector product based on this and the values of x that we've already calculated. And of course we divide by the pivot element as well. So that's the back substitution. And we put the whole thing together. That's it. That's how we do Gaussian elimination in MATLAB. And apart from the fact that we're setting up things here and maybe creating an augmented matrix, there's 5, 6, 7, 8, 9, there's 10 lines of code. It's not very much. It's good value from that point of view. It's not going to take you a long time to... Oh, well, it could take you a long time to come up with this. It's taken us a long time to go through it in the lecture. But once you've got this done, then that's it. And as long as you can convince yourself it works, then you're fine. So, that's the algorithm for Gaussian elimination. And I said yesterday that there's a problem. If one of the coefficients on the diagonal is a 0, you will get to a point where you've got to pivot about that point, and you've got to divide by 0. And all of a sudden, everything falls in a crashing heap because you can't divide by 0 and expect to get any sensible answer. So naive Gaussian elimination is naive, and you should never use it. But if we've got two equations, let's say AX plus BY equals 1 and CX plus DY equals 3, if we swap the order of these equations, have we changed the system that we've got? Well, of course not. We've got the same two equations, it's just that we call this one equation 1 and this one equation 2. Now we're going to call this one equation 2 and that one equation 1. Remember that our augmented matrix is exactly the same as our equations. So if we swap two rows in our augmented matrix, we haven't changed the system we're solving, we've just changed the order in which we're specifying our equations. And that's a very important concept, okay? Because it means you can swap rows in this augmented matrix and you haven't changed anything. Why is that useful? Well, it means we can get rid of that 0 from the diagonal because we're going to swap another row into that. We'll actually come and actually do that in just a second. This concept of swapping rows to get rid of zeros that are on the diagonal is known as partial pivoting. And it's called partial pivoting because it is also possible to swap columns in the system. That just changes the order of your variables. So instead of AX plus BY, you've got BY plus AX. Okay, it's a little bit trickier to swap columns, but you do it. You just got to change the order of the x's in the right-hand side, or the unknown vector. So we only ever do partial pivoting. We only ever swap rows in the augmented matrix. Okay, so the basic idea behind partial pivoting is, let's imagine we've got this system here, and the very first row has got a 0. We know that we can't do any pivoting with this 0. So what we're going to do, if we actually want to come up to a new equation for equation 2, just going through the Gaussian elimination procedure, the new equation will be equal to the existing equation minus 4 divided by 0 times the first equation. Okay, it does not compute, doesn't work. Okay, the partial pivoting will get rid of that. So this is what we choose as our pivot in naive Gaussian elimination. Just swap row 2 and row 1. And this is our set of equations. Okay, we've just reordered them, 2, 1, 3. But now we've got a 4 in the pivot, and we're safe. Okay. Now, the way in which you do partial pivoting, in principle, you can swap it with any row where there's a non-zero element. Doesn't matter. But the mathematics suggests that you're always better off to put the row which has the biggest number. Okay. So, generally speaking, with partial pivoting, if you're a pivot row here, you'll look down and find the biggest number below and then swap that row with the row that you don't want. Okay? There's just advantages to doing that. The matrices that you end up getting are better conditioned. So that's partial pivoting. Then you go ahead with Gaussian elimination as normal. So all this would do to that bit of MATLAB code we had a minute ago was add each time we do a pivot row, we just check to make sure the pivot's non-zero. If it's 0, then we swap it with one of the other rows, and then we keep on going. Okay, so there'd be another sort of 3 or 4 lines of code in there to do partial pivot. So that's everything you need to know about Gaussian elimination. Okay, and I'm hoping that you could all go away and code up your own Gaussian elimination function in a matter of minutes without looking at the lecture notes. Looking at the lecture notes, I'm sure it'll be pretty easy. Of course, as with everything in MATLAB, there's all kinds of other ways of doing similar kinds of things with inbuilt MATLAB commands. I think this has probably already been said before, but MATLAB stands for Matrix Laboratory, and it's actually really, really a powerful tool for dealing with matrices and matrix problems. The canonical matrix problem is AX is equal to B. Practically everything you do in numerical analysis in some form or another can be reduced to the solution of this equation here. For big computational problems that you might end up doing in your career, this matrix here might be have millions of rows and millions of columns. It might be truly enormous. In fact, so big you can't actually store the whole matrix, you can only store the bits which are non-zero. And that's a very common problem. You've got to use some very sophisticated techniques to invert systems like that. You can't use Gaussian elimination, it's too inefficient. But Gaussian elimination, nevertheless, is still good for smaller types of problems. So if you've got this problem here, we can solve it using Gaussian elimination that we've just done. But if you don't want to code this up, or you're running really short of time and you've got to get something working, how can you do it in MATLAB? There are two basic ways of doing this. The first is to use what's known as matrix left division, and the second is by actually calculating the inverse of the matrix. So there's a command in MATLAB to actually do that. Well, I've said down here, matrix left division is better. We'll go into a little bit more detail as to why. Let's have a look at how we actually do this. So let's look at a really simple linear system. It's just a 2 by 2. The matrix A is going to be equal to 2, 4 in the first row, 3 minus 2 in the second row. There, we've got it there. The right-hand side is minus 1, 1. To calculate x, using MATLAB, we just say x is equal to A backslash B. That's just the syntax for matrix left division. You don't need to know how it works or what's going on. This thing here is actually a MATLAB function, and it will use its own technique to actually do this computation. But you'll get x. X is equal to this, and can I advise you always, if you're calculating something like this and you come up with a solution, just shove it back in the original equation. Does it actually satisfy it? So multiply A by X, do you get B? It's a really simple check, but again, you might find, oh gee, I've made a mistake in my Gaussian elimination. I've multiplied by the pivot instead of dividing by the pivot. If A times X is not equal to B, it means you haven't found the right X. And something wrong with your algorithm. So that's just a really good check to use. So, you know, MATLAB function's a black box. It does something. In fact, your own function you can treat as a black box once you've written it and you're convinced it's working. You never need to know again what's inside there as long as you know it works. You can just go away and keep on using it for the rest of your time at Monash if you choose. MATLAB's left division is exactly the same kind of thing. MATLAB basically finds the best way to solve the linear system with this operator. You don't need to know how it does it. You just need to know that it works. The other way of looking at things is to actually calculate the inverse of the matrix A. So just to remind you again, if we have a matrix A, we define the inverse as being that matrix that when we multiply them together in either order, either A to the minus 1 times A or A times A to the minus 1, we get the identity matrix. And the identity matrix is the matrix that has ones down the diagonal and zeros everywhere else. So how we get from AX equals B to a solution is we multiply both sides of this equation by A to the minus 1. To get this, we know that A to the minus 1 times A is just the identity matrix. The identity matrix times a vector is just the vector. And so we've got our solution. So if we can find A to the minus 1, we've solved our problem. This is the other way in which you can solve it in MATLAB. And the way MATLAB does that is it's actually got a function that will calculate the inverse matrix for you. And the syntax is exactly like that. If you just pass the matrix in, the resultant is the inverse. However, unless there's a good reason why you need the inverse matrix, maybe you actually want it for some particular purpose, calculating it to calculate the solution to a problem like this is generally not very efficient. There are two reasons for that. Left division is more efficient and more accurate. It's more efficient because it actually uses something like Gaussian elimination to calculate the inverse. To calculate the solution, and that takes a lot less computation than actually calculating an inverse. Calculating an inverse is a very, very expensive process. Okay, so it's more efficient. It takes less time because there's less computation, and it's more accurate because there's less computation. There's less round-off error. Okay, so you're more likely to get a better solution by using the left division. So that's it. Matrix left division, matrix inverse, programming, partial pivoting. Next week there's going to be a couple of revision lectures, as I've already mentioned, and that is the end of the slides.